Alright, welcome back. This is Computer Science 305 Programming Languages. This is ML version Series 4, Part 2. And we're going to be talking about type constructors with parameters and recursively defined type constructors. So, we already showed some type constructors with parameters. We showed value constructors with parameters before by using the of operator. Now we actually want to talk about how we can actually have type constructors themselves with parameters, right? So now some type constructors can also use parameters. And so, for example, we can create a data type which takes in some a option equals none, right? And then sum of a, right? So our two options are none and sum, right? Sum value type has the value constructor has a parameter which is also some type A, right? Whereas our data type option has some type A as well. So parameters of type constructor are type variables which are used in the data constructors of the result, a new polymorphic type. So, for example, we can use this, right? Because we have a polymorphic type, the comma a, the apostrophe a, and this gives us the ability to construct the polymorphic types as we see down here, where we have some having a real option, right? 1.5 and 123.4, where none just has nothing, right? And then we can also have a string option, which is hello and world. So if we were to run this, right? So option is what we're creating. That's the data type, and so we can create a sum. Well, we'll go down and work an example. So, for example, sum 4. Which creates an int option, right? We can create sum 1.5, which creates the sum 1.5 real option, sum hello, which creates the string option, sum pig, as it shows there in the slide, right? And we can do all sorts of different things, right? Type constructor parameter comes before the type constructor name, as we saw here with option. Apostrophe a, right, which tells us it's a polymorphic type that is not that's constricted by equals op, right? Tells us that we can take in any type, and then it's used here with sum by being the parameter for that data type constructor. So we have types apostrophe a option and int option, just like apostrophe a list and int list, right? So the apostrophe a is just replaced by an actual type, making whatever type we're looking at polymorphic. So we can also use the uses for option, right? Uses for option are, like, for example, predefined type constructor in ML. Used by predefined functions of your own, right, when the result is not always defined. So, for example, if we create a function opt div, right, which will divide options. So, for example, we have a function opt div ab, takes in which is currying, right? So bear that in mind. So we say if b equals 0, then none, else sum a div b. If we do that, right, it returns this curried function, right, that takes in an int, a function that maps an int to an int, and then it maps that function to an int itself, int option, actually. So if we do opt div 7.2, right, we return sum 3, right? Because it's actually 3.5 rounded down, or truncated. And so if we do opt div 7.0, which would be undefined, right? You can't divide Actually, it was B. A divides B. So be dividing anything into 0 be 0. which returns none, right? So we can see that we can define these functions for our defined types as we expected. Now let's take a look at a bit longer of an example, bunch, right? So we create a data type which is polymorphic, bunch equals, and then we create one of X or a group of X list, right? So we have two different possible underlying data types here. We either have just an individual of what the input type, or a list of the input type, right? So it's either a thing of type procedure X, or a list of things of type procedure X. So as usual, ML infers types as necessary. So for example, if we create 1.0, it will infer that we're really referring to a real, right? A real bunch, right? On the other hand, if we create a group of true, false, right, we get a value which is a bool bunch, right? So it's bool bunch, but it's really an underlying list of boolean, right? But that underlying implementation, of course, is hidden from the programmer. So our polymorphic example, right? We can say, let's say we create a function size. So if we get a 1 we don't care what the actual type is, right? We just refer 1. Otherwise, we define size. If it's a group X, then we say is the length of X, right? We assume here X is a list. We do that, creates a size which maps some unknown type A of bunch to an integer. So we operate this. We say size on a 1.0, right, should return an int 1, right? We say size on a group true, false, it will be an int 2, as expected, right? ML can infer bunch types, but does not always have to resolve them, just as with list types, right? The underlying resolution didn't have to occur because it was just handling it based on the one or group, and beyond that, it didn't actually care about the size. So we can also do one without polymorphism. For example, right, in the previous example, we were operating in a polymorphic way. Nothing that we did was type dependent. None of the operations were type dependent. In this next example where we do no polymorphism, right, it's that we're operating a sum. So we say sum 1x, right, equals x, or if we have sum on a group, x list equals fold r op plus 0 x list, right? So the plus operator we know is defaults to finding is for the integer addition, right? It can be for real, but it will default to integer without us telling, without us explicitly informing ML what type we're working with. So if we execute this, it automatically assumes int bunch mapped to an int. And so ML, and as it says here, we apply the plus operator through fold r to the elements. So if we were to operate this, say sum 1.5 would return 5. But if we say sum on the group of 1, 2, 3, as we all know, that is 6, will return 6. Right. So ML knows the parameter type must be of type int bunch. But it knew that well before we gave it any actual values. So then we can actually recursively define our type constructors. This is kind of the interesting part of this whole thing. So the type constructor being defined may be used in its own data constructors, right? And so we have data type int list, and what that's going to do is we have either int nil or int cons of int of the type int by int list, right? So what this is basically going to do is we can have just an empty list, right, which is int nil, and then we're grouping. So if we create an actual list 1 2, it's actually an int cons with a value of 1 surrounding an int cons with a value of 2 surrounding an int cons that's an int nil. Surrounding an int nil, right? So think about this. It's very similar to how like lists and the cons operator works, right? If you want to create a list of one item, you cons that one item with nil, right? So if I wanted to create a list of 1, and the int list containing just 1, I can cons that with nil, and that gives us a list of 1 item, right? So this is really saying that we have a list 1 cons with 2 cons with nil in the example here, and so that gives us 1 2. But if we want to create our own data type, the int list, then we can say data type int list, right, equals, and then what we're going to do is we're going to define it as int nil, right, the base, or int cons of int times int list. And then that gives us the capability to actually construct these things, right? So now, if we want to construct this, we have to do this by essentially first we'll take a look at what is an int nil. So we have an int nil, right? This returns an int nil, and that's it. If we say int cons, right, 1 int nil, right, this creates an int cons containing a 1 and an int nil. We can do the same thing. We can say int cons 1 int cons 2 int nil, right? And this creates the actual list that we were trying to create in the first place. Interesting enough, that this is actually very reminiscent of how lists are created inside of Lisp itself, and it's disturbing to think about. So the int list length function, if we were to create one, right, would be basically the function that we see here. So function int list length int nil. Actually, you know what? I'm going to stop doing this for now, and we will go ahead and create something up here. We'll call this, we'll close this thing. We don't need that open. New file. We'll call this int list dot SML. So we'll actually we'll reconstruct that data type. Data type int list equals int nil or int cons of int times int list, right? So now we have that thing defined. Now we can create the function. So we say function int list length. So if we have int nil, right, equals 0, or we have int list length int cons underscore tail, right? So now it's very similar to how we actually were, the patterns we were matching for a cons pattern. So then we can say, for this, we can define it as 1 plus int list, that'd be int list length of tail, right? The recursive call. So then we can define a second function list length nil equals 0, or list length list length underscore cons tail equals 1 plus list length tail, right? So if we're looking at this, what we're showing here is basically this is the int list length function, and this is a regular list length function. Very simple, easy to do. We wrote them essentially exactly the same way. Alright, if we were to run this, save it, we say SML or polyml on the file that we care about, and actually I need to change that directory mliv. We say sml in list, right? So we have that defined, and now we can execute. We create our int list. We'll say val list equals, and it was int list. Oh, sorry, int cons, and then it would be 1 int cons, 2 int nil, right? This would be the list 1, 2, right? And then we say int list length, and then we int list length on list, and it gives us 2 as we expected. So that's great, and it works really well for integers alone. It's kind of dirty to have to build this up as well as we did. But now let's say we want to actually create just a parametric list type, right? So it's parametric in that it can work almost exactly like a list of any type, right? So what we could do is create a new file, call this parametric list.sml, and then we'll create a data type, right? Data type element my list equals, and then we want the nil for it, and then we want the cons, which includes a type element times an element my list. Alright, so parametric list type, almost like the predefined list. ML handles type inference in the usual way. So if we were to run this right, Control Shift S, go here, Control D, and we operate this. We say SML, and we say parametric, right? So we've loaded up. We say cons 1.0 nil, and we get a real my list, right? We say cons 1, cons 2 nil, and we get an int my list. So now we can actually handle, it doesn't have any operations, right? But at least we have the capability to handle any different type. So so we want to create some list functions, right? So let's do that up here. So maybe we say function my list length nil equals 0, and then my list list length, and we say cons underscore tail equals 1 plus my list length tail, right? Maybe we want to sum things, so we say function add up nil equals 0, add up we say cons head tail, right? So if it's nil, we do nothing, right? It's the value 0. We saw this already. We already created an add up function earlier. We're just making it for our new our new type that we're defining. So we say head plus add up tail, right? Nice recursive definition. Looks really good. Now this works almost exactly like it would for a predefined list type constructor. Of course, to add up a list, you would want to use fold_r, right? So we define that. So we need to create a fold_r for our actual list. So let's create that function. So my fold_r fc nil, right, equals c, or, so I'm going to define that, or my fold_r where we have fc and then a cons of ab. Then we want to say that's equal to f of a my folder fcb, right? So it's a nice curried definition of this. Should work really well. Let's go ahead and take a look, right? So we can now add up an int my list with my fold_r with the op plus using 0x. The remaining difference is that we don't have the cons operator, the double colon, right? Instead we have cons. So cons that we define is not an operator. So what we'll do is we're going to run this first. And so we run it again. Right now we can literally try this out. So let's say we want my fold R. We say off plus 0 x, and then for x instead. Actually, let's define x. We'll say val x equals say cons, and we'll give it a 1, which is cons with a 2, right? Which is cons with a 3, followed by a nil, right? So now we have now we have that int list all built up. It looks great. And so what we can do is we can then say my fold R equals my fold R off plus 0 and let's say x. Theoretically it should work. 6 looks great, right? Everything works, no problem. We can also use add up on x, and it will also give us 6 as well. So we have this thing nicely defined. It looks great. We've created everything we need to be able to do the work that we need to do, and we have a significant portion of the necessary concepts to be able to solve the final lab, the lab. Pretty easy day. Now, if we really want to do this, we then can make operators, right? So ML allows new operators to define. So, for example, we have infixer 5 cons, right? Infixer, so we say 1 cons, 2 cons, nil, right? So we can actually treat cons like it's some sort of magical cons operator, like the double colon, right? So if we were to define this up here, so we say infix are 5 cons, all right? Good times. So if we do this, we rerun it. Now we can say 1 cons 2 cons nil. Okay, we'll say actually let's assign that to value x. Val x equals 1 cons 2 cons nil, and that gives us the list that we expected, right? Now we can actually execute this and be able to solve. I believe we can use the my fold R. We say op plus, and then we can our C was 0, and then we can execute on x, and lo and behold we get 3. So now we're starting to define our language within a language, and it's looking great using types. So let's say we want to create another type of data, the binary tree, right? Binary tree is simply, we have any node where a node can have no more than 2 children, right? And there's a root node which has no parent. So if we want to define this, right, and then essentially every node is basically a tree, a node is a component of a tree which has a left and a right subtree. So let's go up and we'll create a binary tree. New file. Call this binary tree.sml. All right. So we'll go ahead and say data type, and it just takes any type of data. So it's polymorphic, right? And we'll say the first type we have is empty, right? So this is just a tree with nothing in it. Or we'll create one with a node. We have another data type constructor called node, which takes in as its parameters a data, right? A data tree times another data times data tree, right? So it has its own value. So it has on the left side as a tree, in the middle it has its own data, and then finally it has on the right its own another tree, right? Possibility, or that tree could be empty, right? Does that make sense? So we create we want these data tree. All right, so pretty simple. We'll go ahead and we'll run that, see what that looks like. We can create a whole bunch of different things. We'll call this binary tree. And so we create it, right? Looks good. So if we want to create empty tree, we just say empty, right? Gives us the empty tree. We want to create a tree, then we say node with two empty subtrees. We say node, which has an empty, and then the value 2, and then empty, which creates exactly what we want, right? And then finally we can create a node that has 2. The root is 2, the left is 1, and the right is 3. And so in order to do that, we can create the tree as follows. So it would be node with a node, and this would be empty. So let's put some spaces in there. Node. There we go. Node, and this has empty, empty, and then 1, empty, and then 2, followed by a node which has empty, empty, 3, empty. Right? And we do that, and then lo and behold, we have exactly what we wanted to see. And so our tree is the 2 with a 1 and a 3. Right? Nice binary tree. Right? So now, as we just said, we can construct them as we just did. And it looks good. So maybe we want to increment all the elements, right? So let's go up and we'll create a function in here to allow us to do that. So we say function incall empty equals empty, right? This would be increment all. So in case you're wondering, increment all. If we have a node that has x, y, and z, then what we say is node increment incall x, y plus 1 and incall z, right? A nice recursive call that will work basically in what we would call a depth first recursive traversal of the tree, right? Because it will go down the right side and then come back up to the parent of that, and then go down the left side, come back. So it's actually what we would call an in-order traversal. Okay, so now we've gotten that built. We go ahead and we'll execute it. So we'll save that. And actually what we'll do is we'll create a nice tree 3. So val tree 1, 2, 3 equals node empty 1 empty, followed by 2, followed by node empty empty 3 empty. Alright, save that, go ahead, run that. Oh, and I made a small mistake. Let's see, where did I make the mistake at? Oh, there it is. We're really bad at spelling, as we can all see, and I caught another one. Alright, I think I got them all this time. So we go ahead, oh, I have another error. Uh, 8.5. Oh, I am inserting a left parenthesis. Let's see. node. Oh, I ended it too soon. There we go. Okay, so here we are. Right, so we have everything built. It looks good. And so what we can do is we can call incall tree 1 2 3, right? And it should show us that we have, instead of root at 2 with a left as 1 and a right as 3, and now it should be a root at 3 with a left at 2 and a right at 4. And that's what we get. We have a root 3, and on the left we have 2, on the right we have 4. And it looks good, right? Okay, so as we can see, so now maybe we want to add all the elements up, right? We want to have a summation capability for this. So let's go ahead and do that. So we say function sum all, right? So essentially we're going to do in order summation of this. So, and luckily sum, as we all know, is associative and commutative, so it doesn't really matter the order in which we do this. So we say sum all node x, y, z, make sure I spelled empty correct, equals sum all x plus y plus sum all z. As I said, it's an in-order traversal, right? Goes down the left, hitting the sum all x as it goes. Each time it gets all the way down to the bottom, there's nothing else to sum. It comes back up, which is this, right? The recursive hits the empty. Then it comes back up and hits the root of that, which is y. And then it goes down the right side, sum all z. As soon as it hits empty, it comes back up. And then it goes back to the, because this would be the right, we'll go back to the next root, and then go down and sum that one, and then go down to the right subtree of there, of that root node. So this will do that. We could also redefine this in a post order or a pre-order way as well. Or we could do breadth first or depth first. All breadth first approach as well. So there's all sorts of different ways. It just depends on how you choose to write this part. Alright? Specifically in this operation. Up above in the inc all, it doesn't make any sense because we're not operating on any, we're not doing anything with each one of these. We could actually visit it however we wish, but it will affect the way the tree looks. So bear that in mind. You'd have to visit them in a different order and then reconstruct the nodes in a strange form. It wouldn't work out very well. So let's not worry too much about that. But we will go ahead and operate this just to see. So we run this one more time. Binary tree. We say sum all tree 1 2 3, and of course we should see 6, and we see 6. All right. Very nice, very slick. So maybe what we want to do is we want to take this tree and turn it into a list, right? So one of the whole points of having, for example, a binary search tree is that we have the ability to flatten it out to a list of just the values. Once we've constructed a binary search tree from an initial list, it will sort it for us. No, wait, that's not what I'm talking about. But anyway, we need to be able to go back and forth from a tree to a list, so we want to be able to do that. In order to do that, we can construct this nice little list approximation, right? And so we'll create a new function called listAll, which if we have an empty, right, it just creates the nil list. Otherwise, we say listAll. We have node x, y, z, right? And then this is going to follow the same in order traversal, which will then say list all x at y, right? Then list all z, right? So we are doing concatenation and then consing with all the previous list all of z. So it's a pretty simple way of doing things, and will give us this capability. And if we run, we can go ahead. We'll run this in just a second here, and to validate that it did work. So we do this. Run. Oh, we have an error. Hello. What did I do? Oh, I didn't put a semicolon. Let's try that one more time. And oh, I keep being the same. Unbound variable or constructor nil. Hello. All right, one more time. Okay, back to where we were. So we list all tree 1, 2, 3, and we call this, and of course we get the list version 1, 2, 3, right? If we just say tree 1, 2, 3, of course we see that it is the nasty constructed tree that we created, but we did manage to create a nice list for that. Now we can do a tree search, right? So now we want to ask ourselves, by creating a function, we say is in tree, right? We actually want to find out if something is in here, and what we do is we say function is in tree x. Now if it's empty, so we're asking is x in the tree, right? If we have an empty, we say false. Otherwise, we ask is in tree x, and then if we have a tree, which would be node left, y, right, and this is just your simple binary search. So if x is equal to y, or else, right, is in tree x left, okay, or else is in tree x right. So essentially we're constructing this Boolean construction, right? We're asking, well, does the value that we're searching for, x, is that equal to the current root that we of the part of the tree that we're looking at? If it does match that, then we just return true, right? Otherwise, we ask, well, is it in x, right? So it's in the left side. If not, if it's false, right? Then we then search the right side. It's not quite the binary search, but it is a tree search. It will walk the tree, and instead of going down just using the binary properties, because this is not necessarily a binary search tree which maintains the properties that everything in the left subtree is less than the root, and everything in the right subtree is greater than the root. So we can't guarantee that. Instead, we without knowing that, without having that stored property, we only can search the tree itself. So, but this will search the entire tree and then find whatever's in there. So we go ahead and save this, and we'll run it, assuming that I don't have any compilation errors. Which I don't. Excellent. So then we can actually ask. Oh yeah, we did get a warning for using poly equal in the binary in our is tree concept right here. So bear that in mind. It'd be less efficient, but we can run is in tree for tree 1, 2, 3, right? Of course, it comes back as false. Is in tree 3, tree 1, 2, 3, which comes back true, right? If we were to create much larger trees, then we would have something interesting. All right. So we've covered so far basic enumeration data structures, more complex data constructors with parameters, more complex type constructors with parameters, and finally we just got done with recursively defined type constructors. So and along the way we've talked about things like how do we create infix operators, we saw a hint of exception handling and a few other things, but none of these things that we're really are focusing on. We're just trying to understand the language itself. So the final video, which is coming up, will be our farewell to ML, and then you guys can be free and may or may not ever touch this language ever again after the lab is done. So I implore you to watch the next video.